Welcome back. This is another video under electrical circuit concepts. In today's video, we're asked to determine the formula for the following network when reduced to a single resistor. So find the formula R for the following network that represents a single resistor. So basically we're asked to find the equivalent resistance of the following circuit and represent that by R. So basically, we're not going to use the value of the resistance or the value of the resistance. We're going to use R1, R6, and R3, and so forth. So we're going to use the variables, R, the symbols that represent each resistor. So let's go ahead. We can start by combining resistors in series or in parallel. We see that the first combination would be 3 resistors in parallel. These resistors seems like they're in parallel, however they're semi-parallel because both resistors are terminated at this terminal. However, on the other side of the resistors, both of them are not terminated at the same terminal. They're terminated at terminal dot and terminal X. So 2 different terminals, so they're not in parallel. So we can go ahead and combine our first 3. So we can go ahead and write 1 over R, and we can call this R equivalent 1 is equal to 1 over R1 plus 1 over R2 plus 1 over R3. We can further simplify this by finding a common denominator. So each of these, so let's just write it like this. So we find the common denominator. So we have R1, R2, and R3. We multiply each of the numerator by, so the first multiplication, we're going to omit R1 from the common denominator and multiply this space by R2 and R3. So then we get R2 times R3 plus, we multiply this numerator by the common denominator, omitting just R2, so we're left with R1 and R3. So then we go R1, R3, multiply the numerator by the common denominator, omitting R3. So we're left with R2, or R1, R2. That's it. So we can further simplify that, or we can just write this, or R equivalent 1 is equal to R1 times R2 times R3 all over R2 times R3 plus R1 times R3 plus R1 times R2. And that is for equivalent 1. So that is R equivalent 1. So we can redraw our circuit. So we have the first resistor, and that is R5. Then we have R equivalent 1. And we have R4. Then we have R7. And then we have R6. So R6 terminates between R4 and R7 and before R5. R6. So as you can see, we can go ahead. Well, we could just write this all as these 3 in parallel with R6. But let's just combine these in series first, and then after that, we combine those in parallel. So let's go and call this R equivalent 2. we're going to combine these three resistors. So R equivalent 2 is basically R equivalent 1 plus R5 and R4. And we can combine that to equal. We can use our duplication tool. Duplicate that. And then by addition, we can move these further back. And because we want to write a common denominator for these two, if we're going to add our equivalent together, we're going to multiply these two by the following. So let's move that. R4 plus R5 multiplied by the common denominator. Let's move that over. Duplicate that up top. There we go. So that's our equation for R equivalent 2. So now we can further simplify this guy and move along. So we can draw that as R equivalent to R6 and R7. So we can combine these in parallel. So again, we basically just add, well, not add because this is in parallel. We're going to use the formula for two resistors in parallel. So basically we're going to have R equivalent 2 multiplied by R6 divided by the sum of both. And that is for these two resistors in parallel. And then we're going to add that to R7. And that will equal the single resistance. We're going to call that. So when we combine these two, we're going to get R equivalent 3. Then we combine these two, we get R equivalent 4, which we're going to call R. So we can do that by using our duplication tool. So you duplicate that and bring that down. So now we're going to divide. And this guy is going to multiply R6. And we're going to sum that guy with R6. So we can simplify this by getting a common denominator for the denominator in this fraction. So if we multiply this guy through, we see that cancels out. So we're then left with the following. We can still just use our duplication tool. Duplicate that. So then the numerator, and this is going to be R6, all divided by the following. And that's plus R6 times, just use our duplication tool again to save some time. Well, let me move this over. And there it is. So basically what we have here is R equivalent 3. So the resistance at the end, so I think I should just erase this and write it so we can see what's going on. So that's basically R2, R3, R2 times R3 plus R1 times R3 plus R1 times R2. And that is R equivalent 3. So that is equal to R equivalent 3. So R equivalent 3 is the combination of these twos. We just used the formula for two resistors in parallel. Now we can just add these two and R7 to get R. So R is equal to R equivalent 3 plus R7. And that's the formula for the single resistance, or the single resistor. So basically we're asked to find the formula that represent the equivalent resistors, the equivalent resistance of the following network. We just found that if we plug each resistance in for the resistors, we can find the equivalent resistance. And in the next video, we're going to add a voltage source and ask a few questions about the problem itself, like find the power in that resistor, or if we had, say for instance, if we add a voltage source, so say this was plus 100 and we ground this side, what is the current through this resistor? Or if the power of this resistor is so and so forth, what would be the current through here? Questions like that. So that's it for today's problem. See you the next one. Bye.